Students, I hope my screen is visible.
Yes, ma'am.
Okay. So we shall be continuing with combination reactions. Combination reactions between two compounds. Combination reactions between two compounds. So as I said, combination means there can be multiple reactants leading to only one product. Okay, that is meant by combination reaction. So combination can happen between two elements to form a compound. It can also happen between an element and a compound. It can also happen between compounds and compounds. So today we will learn the examples of combination reaction between two compounds. The first being ammonia NH3, which is a gas, ammonia plus hydrogen chloride. This is also gaseous. It will give us ammonium chloride. We all know it's a sublimable substance and it is in the solid form. Okay, it's a very common reaction where two gases give you one solid product. Next example can be calcium oxide. Calcium oxide. Common name of calcium oxide can also be quicklime. Okay. When it reacts with carbon dioxide, it will give us, so calcium oxide is solid and carbon dioxide is gaseous. So the reaction takes place in such a way that the carbon dioxide reacts on quicklime. So that means when we pass carbon dioxide over quicklime, we get a solid which is calcium carbonate. Calcium carbonate is solid. We also call it to be milk of lime, or it's a constituent of chalk. That's the common name. It's a constituent of chalk, but the common name is milk of lime. Going over to the third example, students. Reaction between ammonia and sulfuric acid. Ammonia in the gaseous form plus sulfuric acid, H2SO4. The sulfuric acid we take is in the aqueous form. That means we take an aqueous solution of sulfuric acid. Students, all of you know that sulfuric acid is an acid in an aqueous solution, because if you do not dissolve the compound in aqueous solution, then the acid will not dissociate to give you H plus or hydronium ions. Unless and until the compound dissociates to give you H plus or hydronium in aqueous solution, we cannot define the acidic nature of that compound, right? So we have to take the solution in its aqueous form, okay? And ammonia, when it comes to ammonia, students, please understand, ammonia, I'm just writing down the structure, nitrogen, and you have 3 hydrogen over here. So can you all tell me how many valence electrons nitrogen has? The atomic number of nitrogen is 7, right? Z equal to 7 means that's the atomic number. So the number of electrons shall also be 7. So what can be the configuration over here, students? For nitrogen, the electronic configuration, 2 in the first shell and 5 in the second shell. So that means how many valence electrons does nitrogen have? 5. So in this 5 valence electrons, it shares 3 electrons with hydrogen. Okay, it shares 3 electrons with hydrogen. It shares means it will also get 1 from hydrogen. If nitrogen is giving 1 electron to hydrogen, or rather sharing 1 electron with hydrogen, hydrogen in return will also share another electron with nitrogen. Now this pair of electron becomes or belongs both to nitrogen and hydrogen. Is this clear, students? Nitrogen shares each electron with hydrogen. Once it shares one electron, hydrogen will also share another electron of its. Now, the both of the electrons, this pair of electrons is shared by nitrogen and hydrogen. This means that nitrogen also enjoys 2 electrons while hydrogen also enjoys 2 electrons. So in a way, you can say that hydrogen can have a stable duplet. And while nitrogen, it has 1, 2, 3, 4, 5, 6 electrons already by now. So 2 more electrons will be there with nitrogen. Now these 2 electrons are known as a lone pair, or we also call it as a non-bonding, because it does not participate in any bond formation, electron pair or lone pair. Now for this lone pair, it can actually behave as a base. All of these I explained to make you understand that according to Lewis, students, according to the concept of Lewis, according to Lewis concept, acids are electron acceptors, while bases are electron donors. So according to the concept of Lewis, we have come across acids being H plus donors and bases being hydroxide donors. That is according to Arrhenius concept. But according to concept of Lewis, which is the most modern concept for acids and bases, acids are nothing but electron acceptors. Any compound which can accept electron can be called as acids. And any compound which can actually donate a pair of electrons can be called as bases. So Lewis acid means electron acceptors, Lewis bases means electron donors. So when this nitrogen can donate electron, it can actually behave as a base. So students, what does a base and acid give you? It gives you salt. It gives you salt, right? Salt and water, but over here the base is not a typical hydroxide containing base that it will give you salt and water. It's a Lewis base. So it will only give you salt. And what will be the salt, students? Ammonium sulfate. Ammonium sulfate. And as you can see, this is actually completely balanced. Is this completely balanced, students? Ammonium sulfate. Is this completely balanced? What is the number of hydrogen over here? 8. What is the number of nitrogen? 2. So I have to put a 2 over here. So now 2 nitrogen, 2 3s are 6 hydrogen, plus 2 over here, 8. So this makes the hydrogen equal on both sides and 1 sulfate radical. So ammonium sulfate is formed, remember, in the aqueous state. In the aqueous state, because when you are passing ammonia through aqueous solution of H2SO4, ammonia reacts with H2SO4 to give you ammonium sulfate salt within that aqueous solution. Is that clear, students? Please tell me. Have you all understood combination between 2 compounds? Students?
Ma'am, could you please repeat what you just said at the end, how it reacts as a base, the ammonia?
See, ammonia, have you understood the configuration of nitrogen and
Yes,
ammonia?
ma'am. Yes, ma'am.
Nitrogen have 2 electrons in the first shell and 5 electrons in the next shell or in the valence shell, right? Out of which 3 electrons are shared by 3 hydrogen atoms. Whenever nitrogen will share 1 electron, sharing means if it's giving into the shared pair 1, it will give 1 electron. It will get 1 electron also from the other atom of the shared pair. So as nitrogen gives 1 electron each to hydrogen, it also gets 1 electron from each of the hydrogen atoms. And in a way, the pair is shared between nitrogen and hydrogen. That means the pair is equally enjoyed between nitrogen and hydrogen. Okay, so it has total of 6 electrons. Remaining obviously will be the 2 other electrons, because nitrogen originally had 5 valence electrons, out of which 3 it's sharing. It's as it's sharing 3, it's also getting 3. So 3 plus 3, 6. 6 belongs to nitrogen, but 2 more electrons are there left among the valence electrons. Now, these 2 electrons which are left they are not being shared, that electron pair is known as lone pair or non-bonding electron pair. And any uh, compound which has a lone pair ready to be donated, okay, when it has a lone pair ready to be donated, then that compound behaves like a Lewis base. Then that compound behaves like a Lewis base. For example, ammonia can donate this lone pair of electrons to H plus, and it can become NH4 positive, ammonium ion. Ammonium ion. What kind of donation will this be? Students, it will be a complete donation. Although it will be a covalent or shared bond, but nitrogen will be the only donor. So I'll explain this concept of bonding and coordinate bonding later. But just remember, those compounds with a lone pair can easily behave as Lewis bases because of their capacity to donate the pair of electrons. Is that clear, students? So
Yes,
ammonia
ma'am.
behaves as a base, acid or sulfuric acid behaves as an acid to give you neutralized salt. Anybody with any more doubts, please clarify.
Ma'am, what did you say that the ones which have lone pairs behave as bases?
Yes, the compounds which can have a pair of electrons which is capable of donation, of being donated,
Yes, ma'am.
is known as Lewis bases.
Okay, ma'am.
Yeah.
Got it.
Now, this is a very concise concept for your standard. I'll explain it in the next chapter, which is acid and base and salt. Okay. Now, let's come to combination reaction between an element and a compound. Combination reaction between an element and a compound. So in combination reaction, students, the first example I'll give you is carbon monoxide in the gaseous state. When it reacts with oxygen in the gaseous state, it will give you carbon dioxide. Students, carbon monoxide and excess oxygen will get oxidized to carbon dioxide. So you can call this to be an oxidation reaction as well. Now, is this balanced, students? No, put a 2 over here and a 2 over here. It will now completely get balanced. So it is a compound which is carbon monoxide and the element oxygen between which the reaction or combination reaction is taking place. The next example being sulfur dioxide plus oxygen. Now, sulfur dioxide we take in the gaseous state and oxygen also we take in the gaseous state and we get sulfur trioxide. We get sulfur trioxide. Carbon dioxide, I forgot to mention, that is also in the gaseous state. Okay. Now, is this balanced? No. You need to balance it. So now I have balanced it. Again, a combination reaction. Sulfur dioxide will further get oxidized to sulfur trioxide. And this is an oxidation reaction. This is an oxidation reaction, a typical example of oxidation reaction. Some few more examples can be carbon dioxide, gaseous, when passed over solid carbon, on heating, okay. Now remember, students, because this has oxygen in it, it can act as an oxidizing agent. Obviously, we are learning about combination reaction, but I've told you that if it is a redox reaction, then you please mention that it's a redox reaction. If it's a redox reaction, even though it's combination, it's decomposition, it's single displacement, double displacement reactions are never redox in nature. But if it is a redox reaction, mention it along with the term combination decomposition, both combination and redox or oxidation, combination and oxidation, like this. So this is the oxidizing agent because it has oxygen in it. Carbon dioxide is the oxidizing agent and carbon over here shall be the reducing agent. And I'll tell you why. Carbon, being the reducing agent, will actually reduce carbon dioxide and carbon dioxide will get reduced by carbon, okay, to carbon monoxide, students. So one oxygen less means it will be the reduced form, right? So carbon dioxide will get reduced to carbon monoxide by carbon. And carbon, while being the reducing agent, what does it do? It snatches away oxygen from the other reagent. It snatches away oxygen from the other reactant. So carbon over here will itself get oxidized to carbon monoxide. So at the same time that carbon is behaving as a reducing agent, it is taking away oxygen from carbon dioxide and reducing carbon dioxide to carbon monoxide. Itself, it gains that oxygen and gets oxidized to carbon monoxide. And carbon dioxide, by giving away oxygen to carbon, okay, itself gets reduced to carbon monoxide. So it is the relation between combination and oxidation. Combination and oxidation. Okay? Okay. Now, students, the next example of this will be nitric oxide. NO, nitric oxide. Plus oxygen. Now, this will give you nitrogen dioxide. Just let me balance it a little bit. This will be balanced as 2CO. And over here, this will be 2NO and 2NO2. Now, students, over here also, oxygen is the oxidizing agent, of course, and it oxidizes nitrogen monoxide or nitric oxide to nitrogen dioxide. So this gets oxidized. Okay, and nitric oxide is a reducing agent. Okay, it itself, by being a reducing agent, it itself takes away oxygen from the element and gets itself oxidized to NO2. So that is how combination reactions can also be redox reactions. Is that absolutely clear, students? Please tell me. Is that absolutely clear?
Yes, ma'am.
Ma'am, what's redox reaction? Can you please explain?
Redox reaction, absolutely, students. Redox reaction will be reduction plus oxidation. Reduction plus oxidation. Redox reaction is where reduction and oxidation is taking place simultaneously. So redox is a combination of both reduction and oxidation. Reduction means removal of oxygen, addition of hydrogen. Oxidation means addition of oxygen, removal of hydrogen. Okay, this is very much clear. Now I have taught you a newer concept of reduction, which is gain of electrons, a newer concept of oxidation, which is loss of electrons, right? But over here in these two examples, let me use the other color pen. In these two examples, as I told you, both are examples of combination reactions, right, students? Both are example of combination reactions. But in case of combination reaction, here also we see a picture of reduction and oxidation. Okay, can you tell me over here which is getting reduced? Which is getting reduced? Obviously, carbon dioxide to carbon monoxide. Whenever you are seeing that carbon dioxide is going from dioxide to monoxide, don't you think that it will be the reactant to get reduced, to have got reduced?
Yes.
And what will be the reducing agent? The other reactant, carbon. Okay, and in a way, what is getting oxidized over here? The carbon into carbon monoxide.
Yes.
And who is the oxidizing agent then? Carbon dioxide. So whichever is the oxidizing agent will give away oxygen, means itself gets reduced. And whichever is the reducing agent will snatch away oxygen, that means itself will get oxidized. Similarly, over here, nitric oxide is the reducing agent. So itself, it will get oxidized by taking away oxygen to nitrogen dioxide. And oxygen is the oxidizing agent. So itself, it will get reduced to nitrogen dioxide because it will be giving away its oxygen, atoms of oxygen. Now, is it clear, students?
So all of these reactions are also redox reactions.
Yes, and you have to mention that. Okay, you have to keep your eyes open. Even if it is just a combination reaction, you know it. You will write that okay, multiple reactants giving you one product means means it's combination. But if that combination is also an oxidation reaction, you also need to mention that along with it. Is that absolutely clear, students?
Yes.
Okay, okay. Now we will start off with decomposition reactions. Okay. Decomposition reaction. First, I'll tell you the definition. Reactions in which a single compound, breaks down to give two or more than two simpler substances. Simpler substances. So what are the keywords over here, students? A single compound breaks down, very important because it's decomposition. We all know the literal meaning of it, which is breaking down to give two or maybe more than two, but simpler, smaller substances. Okay. So can we say that decomposition is just the opposite of combination? Because in combination, there is a multiple reactant on the left hand side with a single product on the right hand side. And decomposition is single reactant on left hand side with multiple products on the right hand side. We can say decomposition are opposite of combination reactions. But you have to remember that the way we decompose compounds has literally many ways are there. For example, decomposition can be done by heat. Decomposition can be done by electricity. Decomposition can also be done by light. So we will categorize different decompositions and learn what they are and the examples. So first, let's study about thermal decomposition.
Are we going to read those salts, carbonate, nitrate, sulfite
Uh,
in this?
since I have already done separately the breakdown of nitrates, the breakdown of carbonates, okay, I'll not
Yes, ma'am.
repeat, yes, I'll not repeat that because you already have the notes of previous notes of that portion.
Yes, ma'am.
But today I will just give you examples based on your NCERT syllabus. Okay.
Okay. Okay, ma'am.
Examples which I've given you in details like lead nitrate, zinc nitrate, magnesium nitrate, silver nitrate, how they break down, sodium nitrate, potassium nitrate, how they break down. So this part you keep it as notes and you study for reference later on.
Okay, ma'am. Okay. Thank you, ma'am.
Welcome. So thermal decomposition are decomposition reactions which take place by absorption of heat. Take place by absorption of heat. Okay. Now, in boards, you get activity-based question. We all know that. So the first activity which comes under decomposition reaction, I'm writing it as 1ST so that you don't get confused between two ones. First activity is thermal decomposition of lead nitrate. Although we have done it in details, I'll just repeat it once more. Thermal decomposition of lead nitrate. So first and foremost thing by which explanation will be easier from my end, I'll write the reaction. Lead nitrate, we all know the chemical formula. This is white in color and crystalline in shape. This is white and crystalline in shape, okay? We take this in the solid form in a test tube and we start heating it. As we start heating it, we slowly see this white color salt is getting transformed into a yellow colored residue. And this yellow colored residue is called as litharge or lead monoxide. Along with the evolution of nitrogen dioxide gas, this is solid, this is gas. Remember, nitrogen dioxide gas, very prominent observation. It's reddish brown colored gas, students. And along with evolution of another gas, you can also give the sign as an up arrow. This is oxygen gas. It is colorless and odorless. Nitrogen dioxide is also odorless, but it has color, which is reddish brown. Now let's balance this. There will be a 2 over here, obviously 2 lead atoms over here also. That leads us to 4 nitrogen dioxide molecules. So the ratio is 2:4:1 between reactants and products. Remembering like this is not important. I just told you. Okay. Now students, remember that we are taking powdered lead nitrate in a dry test tube and we are holding it near the Bunsen flame with the help of test tube holder. Brown fumes of nitrogen dioxide are found to evolve with a yellow residue. What do you mean by residue? Something that is left behind after heating a salt behind in the test tube, okay? And we get a yellow residue of lead oxide left behind in the test tube. And this is the following reaction, okay? So students, what are the observations over here? The first observation is we get a yellow colored residue with a evolution of reddish brown colored gas and a colorless odorless gas which can rekindle a glowing splinter. The reason being oxygen is a supporter of combustion, which can rekindle a glowing splinter because oxygen is a supporter of combustion. So it will rekindle the glowing splinter. So these are the 3 observations. Observation A, observation B, and observation C. Fine. Okay. And along with it, it's a decomposition reaction which happens or which occurs with the help of heat, students. Now let's come to the next decomposition reaction, the second one, which is thermal decomposition of ferrous sulfate.
Ma'am, can we also mention that it is endothermic?
Very good. Very good. Endothermic, and you can absolutely mention it. Okay. So thermal decomposition of ferrous sulfate. Students, common name of ferrous sulfate is green vitriol. I'll tell you why it is green in color. Okay. Vitriol means it's bitter to taste. That's why it's vitriol. Now, students, when you take a very small amount of ferrous sulfate crystals, it is crystalline also in a dry test tube. Okay. what happens is ferrous sulfate in the crystalline form, and when it is green in color, it is because it is containing 7 molecules of water, which is loosely bound with it. Loosely bound 7 molecules of water. Now the 7 molecules of water, which is the hydrated form of ferrous sulfate, makes the salt to be crystalline and gives a color to it. That's why the water molecules is known as water of crystallization. So remember, only and only when the ferrous sulfate salt will have 7 molecules of water molecules loosely bound around it, it will give or impart a green color to the ferrous sulfate salt and give a crystalline texture. That is why the water molecules is known as water of crystallization. So initially when you will heat it, remember, instead of ferrous sulfate breaking down, it will first leave the or make the water molecules vaporize. So we will get ferrous sulfate salt plus 7H2O. Now as soon as the water of crystallization separates out, we will get back the anhydrous. Anhydrous means without water. Anhydrous form of amorphous. Amorphous means powdery. Because see, without water molecules from crystalline, it will have an amorphous shape. That means no shape, powdery form. And white colored ferrous sulfate. That means it's only because of the water molecules that it is green in color, else it will be white, that it is crystalline in shape, else it will be amorphous, and we call it hydrated, else it will be anhydrous. So anhydrous, amorphous, white, these are very important technical terms that you need to remember. And further, if you heat the test tube very strongly, the green colored ferrous sulfate will first lose water molecules and the color changes to form anhydrous ferrous sulfate. Anhydrous ferrous sulfate on further heating. So I'll write further heating over here. On further heating, anhydrous ferrous sulfate will give us, on further heating, anhydrous ferrous sulfate will be giving us 2FeSO4. Now that's the reaction. 2FeSO4 in the solid form on further heating will give us Fe2O3. Fe2O3 is ferric oxide, and students, mostly ferric salts are reddish brown in color. Ferric oxide plus evolution of sulfur dioxide plus sulfur trioxide. Now students, sulfur dioxide, this gas has a smell of burning sulfur. So remember, ultimately, when you write that what happens when ferrous sulfate is heated, you have to write this reaction and further this reaction. Only then your answer shall be completed. Only then
Ma'am,
your answer shall be completed.
I'm under FeSO4, you have written anhydrous and after that
Amorphous.
amorphous. Okay, thank you, ma'am.
Yes. Amorphous. Amorphous.
Okay, ma'am.
Okay. Now let's go on to the next one, which is copper sulfate. The next one is number 3. Copper sulfate dot 5H2O. Okay, this is blue in color. It is crystalline. Why, students? Because in the hydrated form, containing 5 water molecules as loosely bound around copper sulfate salt, it will achieve a blue color and a crystalline shape. And when we heat it to something around, say, 100 degrees Celsius, okay, we will be getting copper sulfate dot H2O. That means 4 water molecules will go off. And this is called copper sulfate monohydrate, students. So it's not that initially all 5 molecules of water will evaporate. 4 will evaporate, 1 will remain, and this will give us something between blue and white. So bluish white coloration, because it has lost a lot of water molecules.
Ma'am,
A bit of blue will turn into white. Just a
Ma'am,
minute.
in the previous reaction, did like when we first heated it, so the the solution, not solution actually, sorry, the amorphous was actually the residue in the first time when we heated it, the ferrous sulfate.
No, this is not residue. When the salt is actually breaking down, then this becomes the residue in the test tube. Over there, that is only the water molecules going off, and there is anhydrous ferrous sulfate. Anhydrous ferrous sulfate, when you further heat, and it actually breaks down to give you oxide and more gases. Gases. So that means residue is the remaining part which is left behind in the test tube after evolution of gases. So ferric oxide will be the residue.
Okay, ma'am. Thank you, ma'am.
Welcome. Very good question. Very good question. Okay. So copper sulfate, first it will give you monohydrate, and then it will be, if we further heat it 230 to 250 degrees Celsius, we will be getting copper sulfate in the anhydrous form. In the anhydrous form, it will be amorphous, obviously no shade, and white in color.
Ma'am, regarding the colors, like if during the boards or during the any exam, like for example, after reaction banana pore, and then you don't know the color of the reaction, like the product. তখন
No, in boards, in CBSC, you will always and only get the reactions which you are acquainted with. Okay.
so they won't give us unknown reactions, right?
No, no, no. Because even if they give you unknown reaction, they can ask you to balance it. But observation, how will you know? How shall you know for an unknown reaction what is the color of the compound formed or of the gases evolved?
Ma'am, a salt is only becomes anhydrous when all the water, when it was previously hydrated, evolves. Like it evaporates. Then only it becomes a anhydrous amorphous salt.
Yes. Once all the water evaporates, it becomes anhydrous, means without water. It becomes amorphous, powdery, and the color totally changes. The color is lost. But students, this is not yet complete. Copper sulfate, further on strong heating, breaks down to give you copper oxide. This is black in color. So we will call it to be black residue. With the evolution of sulfur dioxide, sulfur trioxide, and oxygen. Let this be 4, 4, 2, and 2. So in short, remember when you're asked to write down the thermal decomposition of copper sulfate pentahydrate, I need the whole answer. First, copper sulfate crystals, because it contains 5 molecules of water and it's blue in color. Initially, when we heat it to a certain temperature like 100 degrees, it will lose only 4 water molecules, but it will still have 1 extra water molecule loosely bound to it. So it will not completely lose its crystalline shape, neither will it completely lose its color. So it will be bluish white. But further, if we strongly heat, now when it loses all the water molecules at a temperature of around 250 degrees Celsius, then we will get the complete anhydrous form of copper sulfate. Now, once no water molecule is there, it is completely anhydrous, it's completely amorphous, and it's white in color. Now, the anhydrous without any water molecule, okay, and the white color and the amorphous nature, when this copper sulfate is further heated, it strongly decomposes, yielding copper oxide, sulfur dioxide. Remember, copper oxide is black in color. Mainly copper salts are all blue, but copper oxide being an exception, it's black. Copper oxide plus sulfur dioxide plus sulfur trioxide and oxygen. So while performing this experiment, keep mouth of the test tube away because sulfur dioxide is not good for health. Is that absolutely clear, students?
Yes, ma'am.
Okay. Now let's come to some more examples of thermal decomposition. So this is the fourth example that I shall be giving you. Calcium carbonate, this we have done, also known as limestone or chalk or milk of lime. On heating, will give you calcium oxide, which is quicklime, with evolution of carbon dioxide gas. To remember, students, carbon dioxide is a non-supporter of combustion. That's how you can test carbon dioxide. Non-supporter of combustion. That means it can, observation-wise, it can extinguish a glowing flame. Opposite of that of oxygen. And that's why it's used in fire extinguishers, where you have soda reacting with acid, giving off carbon dioxide, which cuts off the supply of air and prevents from further burning. Okay. More decomposition reactions. Potassium chlorate, KClO3. Remember, students, potassium chlorate is from K1 plus and chlorate ClO3 1 minus. Crisscross. So this is chlorate ion. Chloride, hypochlorite. Okay. Perchlorate. So that is potassium chlorate, students, for y'all. When you heat it, remember to do so in presence of a catalyst. So you can also call it to be endothermic and catalyzed reaction apart from thermal decomposition. So you can call it to be endothermic. Endothermic, catalyzed, and thermal decomposition. These are the three types of, headings that we can give over here. So KClO3, it will break down to give you 2 potassium chloride. So keep a 2 over here plus 3O2. So students, remember this particular reaction is used in the lab preparation of oxygen gas. Lab prep of oxygen gas. So it is one of the very important methods for preparing oxygen gas in lab by decomposing potassium chlorate into potassium chloride and oxygen gas. Please remember this, where manganese dioxide is used as catalyst with potassium chlorate. Okay, the reaction is used for the lab preparation of oxygen gas. What about the next one? Zinc carbonate. On heating, zinc oxide plus carbon dioxide. Decomposition of copper nitrate. It's same as lead nitrate. Copper nitrate. It will give you copper oxide plus nitrogen dioxide plus oxygen. Remember, this is black in color. And that is reddish brown in color. And the last one, colorless, although it can rekindle a glowing splinter. So copper nitrate will give you copper oxide plus nitrogen dioxide plus oxygen. Okay, copper oxide is black, oxygen, nitrogen dioxide, brown. We can balance this as 2 CuNO3 whole twice, giving you 2 CuO. That's it.
Ma'am, what is the color of copper nitrate?
Copper nitrate, very good question. It's blue in color. Most of the copper or cupric Cu2 plus salts are blue in color. Copper sulfate, copper nitrate, copper chloride. Only copper oxide and copper sulfide are black in color. Decomposition of potassium nitrate, as I've already taught you this decomposition is very different. NO2 plus O2. So this is potassium nitrate. Yeah. Potassium nitrate will not break down in the usual way. It will rather break down to give you potassium nitrite and oxygen. Okay, now let's balance it. 2 and 2. That's it, balanced. Okay, students, we have electrolytic decomposition and photolytic decomposition. Remember that electrolytic and photolytic decomposition, they are also very important along with thermal decomposition. Electrolytic is with the help of electric current and photolytic is with the help of sunlight. So decomposition can take place with the help of heat, electric current and sunlight. So students, can I continue again next class?
Yes.
Okay, just a minute.